now? Entama, explain me.
Yes, sir.
Okay, right now displayed. Okay. What is the slide you are seeing? What is the matter on the slide? Please read it.
Properties of fluids,
Ah,
viscosity. The top
ah,
layer,
yes.
viscosity. The
Okay.
top layer causes a shear stress on adjacent lower layer, while the lower layer causes a shear stress on the adjacent top layer.
Hmm.
This shear stress is proportional to the rate of change of velocity with respect to y. It is denoted by the symbol tau called tau.
Oh, yes.
Mathematically, tau is directly proportional to du by dy, or
Ah,
tau is equal to mu du by dy.
okay. Yesterday we discussed this. Okay. Whenever we can divide the fluid film into different layers. Okay. In between, we can select any layer for our consideration. Okay, for example, you could just assume a fluid film is divided into 5 layers. Okay, from bottom to top, we can count. Bottom very first layer, which is adhere or stick to that surface or a ground, is layer one. Over layer one, layer two is there. You just assume. Over layer two, layer three is presenting. Over layer three, layer four is presenting. Over layer four, layer five is presenting. Just for our assumption. Okay. See, among these layers, all the 5 layers will experience the shear resistance, shear stress by the adjacent layers. Okay. First layer will experience the friction or resistance to the fluid flow from layer 2, and layer 2 will experience the shear stress or frictional resistance from layer 1, okay, on the bottom side, and layer 3 on the top side. Okay, if you consider layer 3, this layer 3 will experience the frictional resistance from layer 2 on bottom side and layer 4 on the top side. Likewise, layer 4 will also experiences the frictional resistance from layer 3 from bottom side and layer 5 from top side. Okay, and also top layer will experience the frictional resistance from layer 4 from bottom side. So each and every layer will experience the frictional resistance to its fluid flow because of the property viscosity. Got it. This shear stress cause is directly proportional to the rate of shear strain. Rate of shear strain. That is nothing but change in velocity to the change in length du by dy. Okay. In the next slide, we can see it. Uh, one thing. Yes. Are you seeing the figure? Hello.
Yes, sir.
Leelavani, are you hearing? Ramya, are you hearing?
Yes, sir. Yes, sir.
Okay. Okay. Here we are seeing 2 layers, which is at a distance of y, and u, which is moving with velocity u. And over this layer, another layer is flowing with velocity u plus du and lying at a distance of y plus dy. Okay. dy is the change in length, okay, represented in a y direction, and du is the change in velocity, okay, represented on the velocity profile. Okay, the ratio of these two is called shear strain, rate of change of shear strain, du by dy. This is also called as a velocity gradient. So the existing shear stress is directly proportional to this shear strain. Tau is equal to tau is proportional to du by dy. So if you remove the proportional relationship, by introducing one professional constant which is called as mu. Tau is equal to mu into du by dy. Likewise, we got this expression tau is equal to mu into du by dy. So from that expression, by cross multiplication, we can write the expression for mu is equal to tau by du by dy. So that means shear stress by shear strain. How can you define the dynamic coefficient of viscosity or simply viscosity? Viscosity is nothing but the property of the fluid, okay, which offers the resistance to the fluid flow. Okay, in mathematical expression, that its magnitude is equal to the shear stress by shear strain. Okay, and come for the another slide. Unit of unit of viscosity. Uh, tau tau by du by dy. Tau by du by dy. Tau means shear stress. Du means change of velocity. Dy means change of distance. Okay. Stress is equal to force per area. Force by areas. Okay. And consider this term. Change change of velocity. Change of velocity, length by time, okay, and change of distance, nothing but expressed in length. So if you simplify this, if simply, okay, area is nothing but length square, okay, force by length square by time into length by time. If you simplify it, we will get force into time by length square. Force unit is Newton, time unit is second, length unit is meter. So we can write Newton second per meter square. This is the unit for dynamic viscosity in a SI system. Okay. Now see the second slide. Um, kinematic kinematic viscosity. Kinematic viscosity is nothing but the ratio between the dynamic viscosity and density of fluid. Dynamic viscosity to the density of the fluid. Okay. This is represented with a nu. Okay. It is seems to be a small v, but it is a nu. Okay. The symbol, this is a Greek symbol, and this is called nu. So mathematically, kinematic viscosity is equal to mu by rho. Okay, and its units is meter square per second. Similar way, if we can derive these units meter square per second. In connection to that viscosity property, Newton's law of viscosity is a very important law. Okay, the Newton experimentally proved this. What is it? Shear stress on a fluid element layer is directly proportional to the rate of shear strain. The constant of proportionality is called coefficient of viscosity. Mathematically, this is expressed. Okay, this is mathematically this is expressed in this form. Previous slide. If once we go back to the previous slide, we can say shear stress is directly proportional to the rate of shear strain. Okay. So if you remove the fractional relationship, we will get a tau is equal to mu into du by dy. Newton law. Newton's Sir Isaac Newton experimentally proved this. Okay. And based on this law, fluid also classified into Newtonian fluids and non-Newtonian fluids. Okay, Newtonian fluids which obey the above relationship is known as Newtonian fluid. So that means Newtonian fluid is a fluid which obeys the Newton law of viscosity. That means in a fluid flow, its shear stress is directly proportional to the rate of shear strain. Okay, and non-Newtonian fluid means the fluids whose shear stress is not directly proportional to its rate of shear strain. Okay. The viscosity vary with the temperature. Viscosity naturally varies with the temperature. Okay, the predominant terminology which affects the viscosity based on the temperature is two. What are they? Cohesive forces and molecular momentum transfer. The viscosity of liquid decreases with the increase of temperature, while for liquids, okay, temperature affects the viscosity. Okay, fluid is means liquids and gases. Okay, what about the liquids? The viscosity of liquid decreases with the increase of temperature, while the viscosity of gases increases with the increase of temperature. Okay, why this is happening means for the case of uh, fluids, cohesive forces and viscous forces we have to consider. Okay, okay. In liquids, the cohesive forces predominates the molecular momentum transfer due to the closely packed molecules and with the increasing temperature. These cohesive forces decreases with the result of decreasing viscosity. Okay, this is thing. For liquids, cohesive forces dominates over the molecular momentum transfer, and moreover, this cohesive force decreases with the increase in temperature. If cohesive forces decreases, viscosity also decreases. And for gases, but in case of gases, the cohesive forces are small and molecular momentum transfer dominates the cohesive forces. With increasing temperature, molecular momentum transfer increases and hence viscosity increases. The relationship between viscosity and temperature for liquids and gases are given with help of one expression. For liquids, mu is equal to mu naught into 1 by 1 plus alpha t plus beta t square, where mu is the coefficient of liquid at T degree centigrade. Okay, T degree centigrade. In poise, viscosity can be expressed in Newton second per meter square or poise. One poise is equal to 1 by 10 ns per meter square or 0.1 Newton second per meter square. And mu naught is the viscosity of liquids at 0 degree centigrade. This is also in poise, where alpha and beta are the constants. Okay. For gases, the expression is mu is equal to mu naught plus alpha t minus beta t square. Mu is equal to mu naught plus alpha t plus beta t square. Okay, this is the mathematical expressions. By saying this, we can easily say that viscosity for liquids decreases with increase in temperature because a temperature term presents in a denominator. Okay, if denominator value increases, definitely that ratio value will decreases. Ratio value will decreases. Okay, and whereas for gases, um, temperature is presented in a expression, not numerator or not denominator. Okay, of course, if by one you can put okay, u is equal to mu is equal mu naught plus alpha t minus beta t square. If t value increases, mu also increases. For gases, uh, thermic viscosity will increase with the increase in temperature. Okay, next go for the next slide. Types of fluids. Types of fluids. There are the five types of fluids. What are they? Ideal fluid, real fluid, Newtonian fluid, non-Newtonian fluid, and ideal plastic fluid. This term can be seen in a coming slide. What is meant by ideal fluid? A fluid which is incompressible and having no viscosity, or simply viscousness and incompressible fluid is called ideal fluid. But there are no ideal fluids available in the world because all the fluids are having viscosity. Okay, that is why there is a no ideal fluid. This is only a hypothetical and a theoretical concept by which we can compare the real fluids behavior. Okay, real fluid means a fluid which having viscosity, which possess viscosity. Okay, and Newtonian fluid. That name itself it is giving. Newtonian fluid means a fluid which obeys the Newton law of viscosity. Newton law of viscosity, or simply fluid in which shear stress is directly proportional to the rate of shear strain. Okay. Then what is meant by non-Newtonian fluid? Non-Newtonian fluid is a real fluid which in which shear stress is not proportional to the rate of shear strain, or simply uh, here Newtonian fluid. Non-Newtonian fluid is a fluid which not satisfy the Newton law of viscosity. And next slide. Next slide. Okay. Here we are seeing an ideal fluid, ideal plastic, ideal plastic fluid. If you see, types of fluids are represented along their shear strain and shear strain and shear stress. Okay, this is the ideal fluid. For ideal fluid, viscosity is zero. Okay, so viscosity is zero. So tau is equal to mu into du by dy. If you put viscosity is equal to zero, then shear stress will become zero. So that is why ideal fluid is represented on a horizontal line. And the next come for Newtonian fluid. Newtonian fluid means whose shear stress is directly proportional to the rate of shear strain. Okay. So if velocity gradient increases, shear stress also increases. This is a linear proportionalship relation. Okay. That is why it is represented between with an inclined line which is passing through the horizon. That means velocity of gradient is increasing, shear stress also increasing. If velocity gradient decreases, shear stress will also decreases. And non-Newtonian fluid is represented with a one curve. Okay, okay. This value is not at all constant. Sometimes it increasing, sometimes it is decreasing. Got it. After a particular point, its value started decreasing. So it is not satisfying the Newton law of viscosity. So such fluids are called as non-Newtonian fluid. Okay, this is the graphical representation of variation of shear stress with respect to the velocity gradient. And now come for the ideal plastic fluid. Ideal plastic fluid. See, this is a fluid in which shear stress is more than the yield value and shear stress is proportional to the rate of shear strain or velocity gradient. See, ideal plastic fluid is represented with the same inclined line, which is parallel to the Newtonian fluid line. But the difference is, but the difference is, what is the difference? Yes, shear stress is more than the yield value. Yield value means zero. So it is having higher value than the zero. So it somewhat its value is greater than the yield value. And after that particular point, shear stress varies linearly with the shear strain or velocity gradient. Such type of fluid is called as ideal plastic fluids. Okay. Now come for the next slide. This small is a single problem. If all of you see this slide, read this slide. If the velocity distribution for a fluid is given by U is equal to 2 by 3 minus y square. in which u is velocity in meter per second and at a distance y more above the plate, or y meter above the plate. So he is asking us to determine the shear stress at y is equal to 0 and at y is equal to 0.15 meter. Take dynamic viscosity of fluid as 8.63 poise. Okay, this is the given problem. How to solve the problem? Next slide. Okay, so this slide first we are taken. We are taking the given relationship between velocity and length, that is given by u is equal to 2 by 3 into y minus y square. So differentiate this expression, use a velocity expression with respect to y. So du by dy is equal to 2 by 3 is the constant. Dy by dy is equal to 1. So 2 by 3 into 1 minus y square, differentiation with respect to y. So n into y power n minus 1. Okay, 2 into y power 2 minus 1. 2 minus 1 means 1. Y power 1 means y. Okay, du by dy is equal to 2 by 3 minus y. And he asked us, what he asked us? Determine the velocity. Where, okay, determine the shear stress at y is equal to 0 and y is equal to 0.15. Okay, so we are calculating shear stress, rate of shear strain, du by dy is equal to dy at y is equal to 0. Okay, so here he mentioned du by dy at y is equal to 0 is equal to, put y is equal to 0 wherever y presents in the expression. 2 minus 3, 2 by 3 minus 2 into 0. So 2 by 3 is equal to 0.667. Are you following?
Yes, sir.
Okay, are you following?
Yes, sir.
Okay, right. Next, du by dy at y is equal to 0.15. So wherever y presents, substitute 0.15. Okay. What is the expression? 2 by 3 minus 2y. So 2 into 0.15. That is equal to 0.667 minus 0.30. So if we simplify it, we will get 0.0367. Right. Now he is asking us to calculate the shear stress at y is equal to 0 and as well as at y is equal to 0.15 meter. And he given viscosity mu is equal to 8.63 poise. 1 poise is equal to 1 by 10 ns per meter square. Point 1 by 10. Therefore, all of you see this conversion. 8.63 points is equal to 8.63 into 1 by 10 in Newton second per meter square in SI systems. Okay. So if you simplify it, we will get 0.863 Newton second per meter square. Now, shear stress. What is the shear stress expression? Tau is equal to mu into du by dy. Take the tau expression. At y is equal to 0, tau naught is equal to mu into du by dy at y is equal to 0. Wherever y presents, put it value. Okay. In at y is equal to 0, y is equal to 0, there is a no y term. So only simply mu and du by value. This is 0.x3 is the mu value and 0.667 is the du by d value, du by dy at y is equal to 0. So if you simplify it, we will get 0.5756 Newton per meter square. And next, shear stress at y is equal to 0, sorry, y is equal to 0.15 meter and is given by, okay, shear stress at y is equal to 0.15 is equal to mu into du by dy at y is equal to 0.15. We calculated this du by dy at y is equal to 0.15. We got 0.367. Okay, substitute mu value 0.863 into dy value 0.367. If we simplify it, we will get 0.3167 Newton per meter square. In this way, we have to solve the shear strain. And one more problem given in. Let us see. In the slide, for the problem statement, calculate the dynamic viscosity of an oil which is used for lubrication between a square plate of size 0.8 meter into 0.8 meter and an inclined plane with an angle of inclination 30 degrees as shown in figure. The weight of the square plate is 300 newtons and it slides down the inclined plane with uniform velocity of 0.3 meters per second. The thickness of the oil film is 1.5 mm. So he is asking us calculate the dynamic viscosity of the fluid. Because see the figure. Oh, there is a one inclined plane. Angle of inclination is 30 degrees, and one plate is sliding on this with velocity 0.3 meters per second. In between inclined surface and the given object, there is one lubricating oil. Okay, and the thickness of this is 0.15 mm. Weight of that plate is 300 newtons. Okay, for this, we have to calculate dynamic viscosity. Next slide. Okay. Write down the given data. We are writing the given data. Area of the plate. A is equal to zero point 0.8 into zero point 0.8. That is equal to 0.64 meters square. And angle of the plane. Inclination of the plane 30 degrees. Weight of the plane 300 newtons. Velocity of the plate is equal to 0.3 meters per second. Thickness of the oil film. T is equal to dy. This is nothing but dy. 1.5 mm. Convert this mm into meters. 1 mm is equal to 10 to the power of minus 3 meters. Okay. Let the viscosity of the fluid between the plate and inclined plane is mu. We are assuming the viscosity of lubricating fluid as mu. And the component of W along the plane is W cos 60 in W because we have to resolve that expression in first year physics in the third unit, especially in kinematics of physics. Kinematics, we have resolved certain velocity vectors into horizontal component and vertical component. Okay, if we consider inclined surface, this is weight component along with the plane is W cos theta. Okay. How to find in simple way means along with the plane means cos function will come. Horizontal component means cos theta will come. Um, Vertical component or perpendicular component means sin theta will come. That is the indication. Hello. Okay. In that way we have to resolve the any vector. Okay? Here the weight component is W cos 60. What is the weight of the body? 300. Okay, 300. Here we can get one doubt. We can get one doubt. Theta is 30 degrees. Theta is 30 degrees. Then here we are representing 60 degrees. How can we can get it? See, go for the previous slide. See, this is the horizontal side. Okay, this is the horizontal side, and this is the inclined side. Okay, there is a weight. Weight is represented with vertical line. Okay, you extend that weight vector until it meets the horizontal line. Okay, otherwise complete the triangle. Close this side also. Close this side. Once we close this side, what will happen? This will get we will get 90 degrees here. 90 degrees. This is 30 degrees and this is 90 degrees. What about this angle 60 degrees? Okay, so here we will get 60 degrees. Understand? So once we resolve it, we will get a horizontal component. This theta will come. Whatever the angle presented here, that angle will come to this weight vector. W is equal to cos uh, cos 60. Here 60 degrees. That is why we are taking 60 degrees. Okay. And come for this slide. Okay. What is the weight? W cos 60. W is 300 and cos 60. So if once we simplify it, we will get 150 because cos 60 is equal to 1 by 2. 300 into 1 by 2. If simplify it, we will get a 150. Thus, the shear force F acting on the bottom of the shear plane is 150 newtons. Because weight is nothing but force. Force unit is Newton, and the weight unit is also Newton. So weight is nothing but a F force. Okay, therefore shear stress is equal to force by area. We got force 150 and area we have 0.64. If simplify it, we will get a numerical value. And also from equation tau is equal to mu into du by du by dy, where du is a change of velocity, u minus 0. Okay, u is equal to 0.3 that meters per second. Dy is equal to thickness. T is equal to 1.5 into 10 to the power minus 3. We converted this into meters. Therefore, tau is equal to 150 by 0.64 is equal to mu into okay. Hello.
Yes, sir.
Yes. Now see we are simplifying. So once if we simplify it, we will get viscosity as 1.17 Newton second per meter square. Okay. See, we can express that value in poise also. If one poise is equal to 1 by 10 Newton second per meter square, 1 Newton per second per meter square is equal to 10 poise. 10 poise. So if you want to express that value in poise, you can multiply it with the 10. 1.17 into 10 is equal to 11.7 poise. This is the simple information regarding this problem. For the understanding, we can see one more problem. The space between two square flat parallel plates is filled with oil. Each side of the plate is 60 centimeter. And the thickness of the oil film is 12.5 mm. The upper plate, which moves the upper plate moves at 0.5 meter per second, requires a force of 980.1 Newton to maintain this speed. Okay, he determine the dynamic viscosity of the oil, kinematic viscosity of the oil, specific gravity of the oil given as a 0.95. Just to try to understand the problem. Two parallel plates are there. Okay, in between these two parallel plates, oil is filled. Okay, and thickness of the oil film is 12.5 meter. Each side of the plate, each side of the plate, each side of the plate is 60 centimeter. The thickness of the oil film is 12.5 meter. Here he mentioned upper plate is moving with 2.5 meters per second. Okay, to maintain this speed, we need 98.1 newtons of force. The case is like that. So he is asking us to find out the dynamic viscosity and kinematic viscosity. Okay, oil specific gravity is 0.95. Okay, this is the given data. Okay. They also mentioned each side of the sphere plate 60 centimeter, nothing but 0.6 meter. Area 0.6 into 0.6, 0.36 meters square. Thickness of the film dy is equal to 12.5 mm. Now convert it into meters. 12.5 into 10 power of minus. Then velocity of the upper plate u is equal to 2.5 meters per second. And the change of velocity between the plates du is equal to 2.5 meters per second. Now, force required to maintain the speed on the upper plate is F is equal to 98.1 Newton. 98.1 Newton. Okay. Now, shear stress is equal to tau is equal to force by area. Force given, area also given 98.1 by 0.36. Put it okay. Now we are assuming let mu is equal to dynamic viscosity of the oil. So by using the above equation, tau is equal to mu into du by dy. Our tau value given 98.1 by 0.36 is equal to mu into this du by dy value. Du is 2.5 and dy is 12.5 into 10 to the power of minus 3. So from this expression, we can calculate mu is equal to 1.3635 Newton second per meter square. Okay. Dynamic viscosity we calculated. And what he asked, kinematic viscosity, he asked. Specific gravity of the oil given. This is equal to 0.95. Let mu is the kinematic viscosity of the oil. Okay. What is the expression for density in terms of specific gravity? Rho is equal to S into 100 or rho of oil is equal to specific gravity S into density of water. Density of water is nothing but 1000. Rho is equal to S into 1000. This is the thing. S is a given value, the problem 0.95 given. 1000 density of water is constant. So we will get 950 kg per meter square. Dynamic density of the oil is 950 kg per meter cube. Now, kinematic viscosity, we are calculating nothing but mu by rho. Okay, mu is equal to what is the value? Mu viscosity 1.3635 If you simplify it, we will get 0.001435 meters square per second. In this way, we can solve any problem. We know the relationship between viscosity, shear stress, and shear strain. We know the relationship between viscosity, kinematic viscosity, and density. We know the relationship between density and specific gravity. By using all these expressions, we can determine the any other required data by using the given data in the problem. Okay. Now I'm closing the session. On Monday, we will meet you again. Okay. You can leave. Thank you.
Okay. Thank you, sir.
Any doubt?
Yes, sir.
Okay. Okay. Right.